Thank you. Well, it's very exciting to be here. I came to CogMIR last year for the first time, and it was really interesting to see this merging of the cognition and computational fields. And it reminded me that in a past life, I was actually very involved in either music technology or computational musicology or whatever I wanted to call it back then. And so over the past year, I've been thinking about sort of bringing back this project that's I haven't really worked on about 10 or 12 years. So some of the stuff might be slightly out of date at this point, but I think it's an interesting idea to think about how we can use some of these tools in corpus analyses or other projects that I'm doing in my lab now or that other people are doing. So I'm going to talk about a software package that I developed to help with automated analysis of musical information. And since then, about 2001, we have new tools like Music 21 that I was talking to people about last year. So I'm also interested in getting feedback from other people who are more involved in this kind of stuff now than my lab has been. There are other tools for automated analyses, and I know Humdrum offers the ability to do certain kinds of things. As far as I could tell at the time, it wasn't well suited for the things that I was trying to work on, but I know some of the people in this room have spent more time working with both of these than I have. So when I decided to give the talk here, I was bringing back some ideas that were inspired from a seminar I took on post-tonal analysis. Because in a previous life, I had actually toyed with the idea of becoming a music theorist. And I since decided that my research interests lie elsewhere. So imagine my surprise when showing up today, I realized we have many music theorists in the room. So I'm sorry if I sort of mis-explain some of the things, but the point of the talk is actually on the analytical possibilities of the software tool, and I'm using this post-tonal analysis just to demonstrate some of the principles. And it's also, those are the questions that I was thinking about a long time ago that sort of inspired the development of this framework. So in this class that I was taking on post-tonal analysis, we were doing a lot of analyzing pitch structure in a way that basically seemed to boil down to something methodical where we would take a certain window and look for a certain grouping of notes and look at the interval content or the pitch content within that window. And in doing all these assignments, I realized that basically what we're doing is taking this window and sort of sliding along, looking at all the notes in here, and we have the G sharp and the G and the B, and then we could see what kinds of patterns that we're finding bit by bit. And it occurred to me that this seemed like a really good way to harness the power of computer automation for analyses. So I was trying to think about what kind of software we could use to maybe do that. So I hit upon the idea as a senior project of doing some kind of automated analysis based on some post-tonal principles we were talking about in this class. And it sort of grew and grew for a while until I ran into this brick wall, which was trying to understand what all these patterns meant perceptually, at which point I started getting interested in music perception as a side project, and that sort of has taken me through the next decade or so. So it's really fun for me to go back and look at some of this stuff, and I look forward to hearing some of your thoughts on this. So in terms of the structure of the talk, we're going to talk very briefly about some background with music theory. The idea is just to set the groundwork for some of the analytical approaches we'll be talking about, but I know people are coming from sort of varying backgrounds, and I just wanted to go over a couple things. As a show of hands, I'm just curious, who's ever taken a class on post-tonal analysis? Oh, okay, fair number of people. Awesome. All right, you can remind me if I happen to miss a couple things. So after going through the overview of the music theory, we're going to talk about the structure of some of the software in terms of the development process, and then go over two proof of concepts that I did just to basically prove to myself that this is actually doing what I was thinking that we we're going to do. And then we'll talk about some of the future directions, because the whole structure of the suite can be applied to any number of different problems. Here we're just going to start with post-tonal analysis because I think it lends itself well to that. So one of the things we'll be talking about are based on interval class vectors, which are somewhat related to pitch class sets. So in the interval class vector, we've got here this string of numbers. It's not actually binary, as I realized yesterday, some of my students pointed out. But what we've got is each place in this string encodes the number of intervals of a certain size that we see. So these are half steps, or one semitone, whole steps, minor thirds, major thirds, or interval sizes of 1, 2, 3, 4, and 5 if you want to get outside of some of the tonal language. In terms of realizing how this would appear on a keyboard, here's one example. If we had a C, C sharp, and an E, that would give us this interval content where we've got one half step, or one interval size of 1, one interval size of 3 between the C sharp and the E, and one interval size of 4 there between the C and the E. This interval class vector isn't tied to a specific place on the keyboard. So if we had this grouping of notes here with the B, C, and the E flat, we have the same interval content because we have the 1, 3, and the 4, or this grouping up here. It's all pointing us back to the same thing. Now, I'm not taking a position on whether this is necessarily the best way to be analyzing music at this point. At the time, I thought it was really cool and fun to take these mathematical approaches, and so I was excited about that. But they do lend themselves very well to serving as this proof of concept for what we can do with this analysis software. So the basic idea with this data structure, to move to a much simpler melody here just to illustrate the point, is that I realized trying to do the analysis based on the notation caused some problems. Because if we were taking, say, a 2-beat window at the beginning, we're fine. But if we're shifting this along, say, by eighth notes, we get to the situation where taking a vertical slice of the score, starting at the upbeat at the beginning, is going to miss that C that happens to be ringing. And so the underlying data structure representation for this is based essentially on the principles of a piano roll style of notation. So as we slide this window along, we get a glimpse or a snapshot of all the notes that happen to be sounding at any given point. In the score, each note is an object, and so we tag all these in the bucket and we can throw them somewhere else, and all the notes retain the properties about the time in which they started sounding, the pitch, and the instrument that played them. So you can take the buckets, normalize the pitch class set, do whatever you want with it, and then trace back the location of each of the individual notes in the score. So in principle, you could change the timbres of the notes if you're playing things back, or do all sorts of different fun stuff with it. Now, in trying to think of the best way of balancing sort of access and then the computational affordances, what I decided to do is everything is based here on a standard MIDI file representation. Now, I went with standard MIDI files because they're just the language spoken by many different devices. There are certainly some downsides to standard MIDI files, one of which is the problem, or MIDI doesn't really even encode timing. Standard MIDI encodes timing in this sort of idiosyncratic way. So I take the standard MIDI file and then import it, creating this virtual score that seemed to work for a number of different files that I tried, except for some real big symphony pieces, which seemed to be more than the program was able to handle at the time. But in principle, this should work for pieces of any size. So the first proof of concept here is based on just an analysis assignment that we had in this class, where we were looking at this Schoenberg example, which is sort of a famous one within the world of these kinds of analyses. He uses a lot of this pitch class set that is called 014 that corresponds to that interval class vector that I showed you before. But the main thing here is you just went through, I typed this up into, I think this was like Finale 98 or something, and sure enough, in an analysis of just the first couple measures, it spit out, these 4 patterns here, which are the ones that are talked about in this textbook as being, instances of how important this pitch class set is, or you could call this an interval class vector in this piece. So I thought that was pretty cool, and I was excited that after a lot of coding and programming, it seemed to actually be finding the patterns that I was, expecting it to find. But then the problems began, because I realized in addition to these 4 patterns, it found another, I think, 8 just in the first 3 measures alone. And so at the end of the day, we have 12 instances just in the first 3 measures. We've got the 4 sort of standard ones, but now all these other ones as well, giving us a nice sort of spaghetti soup of a mess here. And this is the point at which I started getting interested in perception without really knowing what the language was to talk about those kinds of things, because it raises this question about, well, we can find anything in this kind of data mining here. Like, what are the patterns we're necessarily perceiving and noticing? And so I remember one moment when I think I talked to Scott Lipscomb, because I took his Introduction to Music Perception class at Northwestern, and he asked why I was taking the class, and I said I wanted to spend a semester learning about music cognition so I could get back to the work with the analysis software here. But as it turns out, it was more complex than could be covered in just that one semester, and so the perception cognition world is where I've been living mostly ever since then. But in terms of trying to understand the significance of these patterns, I was realizing we're finding way too many of these, and so we need some kind of way of looking at the overall structure of a piece in a different way. And so I started doing this sort of seek and find approaches, where I went through, and if we're looking at the interval class content in terms of, or the pitches in terms of these trichords, essentially for 3 notes we have 12 different ones. And so I wanted to do a comparison of how much more this 014 one was showing up, which I thought should be in there more relative to everything else. Because this is the case, we're just going to find 150 patterns for everything. And so on the y-axis, you get an idea of how big the total number of patterns we're finding going to be, because we're looking at up to 1,500 occurrences here. And so for the 014, which is the one that we were expecting to find the most of, we found a very high number of occurrences. Curiously, for all the other ones, we found a fair number as well. And so there's definitely a bit of noise in terms of trying to seek out these patterns in the system. But I thought it was sort of neat that the one here that I thought should be in there the most, and that is talked about as being the most important, is at least mathematically the most prominent one in there. That doesn't necessarily mean it's the most perceptually salient, but in terms of the mathematics, I thought that was neat that it worked out that way. So in terms of trying to understand how to move forward with this, I realized that if we've got this technology together where we can build a virtual score from a MIDI file, we can take this window and just sort of slide it along there, then we're not limited to just sort of seeking out one particular pattern or even one particular kind of pattern. Because once you take the notes in a bucket, so to speak, we can move them around in a different way. We can actually then take some kind of unique identifier based on the combination, throw it into a big hash table, and then do basically a big inventory of everything that we're finding. And so I think that's a big shift in the kind of work that we're doing with this, because we go from sort of seek and destroy, tell me how many patterns you find out there, to sort of, okay, analyze on a certain principle and just tell me what you're going to get. So as another proof of concept, I went back to another discussion point in this book and used this very short piece by Webern from 5 Pieces for a String Quartet. And went through, and rather than trying to find one particular pattern, actually recoded things to use the same principles and just catalog all the different kinds of pitch combinations that were coming through. Now, and again, looking at the pitch structure might not be the thing you are most interested in the music, but you could fairly easily rejig some of the routines to look at any other kind of property. So now we're looking at what I call a sort of smarter kind of pattern detection. And so on the y-axis now, instead of the raw number of occurrences, we're looking at things as a percentage of the overall totals. I broke things up because the text sort of talks about this piece in ABA. Obviously, we're on a very abbreviated scale here because it's rather short. And so I was interested in how the pitch material varies between the A and the B sections. Now, these are the 3 interval class vectors, or the pitch class sets, that are discussed as being the most prominent. And so it's interesting that in this first section here, when we graph out all the different kinds that we're finding, you can see the 3 certainly occur more than the others. We go into this middle section here, they're happening a fair amount, but the frequency of them drops. And then when we get to the third section, we can see, at least for some of them, they have to be rising again. So this would take someone with more theory chops than I have to really interpret necessarily what this means. But from a computational standpoint, I was pretty excited by this because it seems to give sort of a new way to just play around with doing some analyses. So in the long run, I think there's a lot of work that can be done with this concept of taking sort of this virtual score representation with the piano roll style and just sliding windows along and taking notes and looking at them in various different ways. And so at one point, I was planning on doing all sorts of future extensions of this, and this has sort of been on hold for the past 10 or 12 years. But I think there's, I don't know, some interesting work that could be done. And I've been thinking more recently about some of the empirical musicology stuff that I've been doing in my lab, which has for the most part been by hand because of some of the complexities of doing these automated analyses. It'd be great if we got to the point where we could do some kind of automated analysis for those kinds of things. And the whole CogMIR seminar and workshop just got me thinking about ways to dust this off and do more things in the future. So in terms of the acknowledgements, we had some funding agencies that fund our current work, although really I realized as putting this together, I have to go back to my undergraduate days when this project was actually supported jointly by the Computer Science Department at Penn State and the School of Music when I was an undergraduate, and then when I started graduate school at Northwestern, I was doing some further development, and then it all just sort of stopped back then. So I think there's some interesting things to be done, and there's probably been, I know there's been a lot of developmental work since then, so I look forward to hearing thoughts and feedbacks and suggestions about the future for this. Thank you.
Time for questions. Yes.
Thank you for your presentation. I was wondering about those input vectors you presented, and I was wondering whether to go for the first example you had where you
So if it was like instead of C, C sharp, and E, it was like C sharp, E, and F?
Yes.
I guess music theorists, I think that gives us the same interval class vector. Is that right? If we had a C, C sharp, and E, it's the same interval class vector as C sharp, E, and F? Yes. Thank you, Theory 345 or whatever that was. Yeah, Rich.
Very interesting stuff. And
Thank you.
pulling out the Strauss book and knowing Strauss's background in his working with Alan Ford, there's a ton of a priori assumptions that go into a post-tonal analysis. And I think that you're engaging some of these very directly. Are you looking for a total catalog of pitch class sets in a piece of work? Or are you looking for instances of the same pitch class set? This kind of cataloging, how many O14s are there? Or are you taking some kind of other approach that perhaps relies on salience? And so what do you imagine? That Opus 11 example is a really good one because you can look at O14s and it'll show you all the O14s, but whether or not that actually makes musical sense in a meaningful way is pretty questionable. And in fact, there's a dynamic progression between different kinds of set classes that makes a lot of sense. They're all kind of moving, wedging apart from each other by semitone, but it's a difficult thing for post-tonal analysis to capture. So I wonder what kinds of limitations you feel or have encountered by adopting this methodological approach.
Yeah, well, that's the exact problem I ran into, and my solution was to move into a different field and not deal with it. So you're right. There's definitely a lot of assumptions. That's why I'm not saying I'm particularly tied to any particular framework of the post-tonal analysis. It's what got me thinking about this, and that's what the examples are for. But I think the interesting thing is you could explore it to test the issue from either side. And you're definitely right. Like, I'm not saying I listened to the piece that's, 60, 70 measures long and hear all 23,000 patterns. Like, I wish I had ears that way, but I don't think even Boulez would be able to. So the question is definitely which are most salient. So you actually get a printout, and I have these somewhere, of like all 15,000 patterns down to the exact note, because everything's an object, so you can trace it back to the score. And at first, I'm getting the numbers for the printout, and I thought there's got to be some kind of programming error, because there's no way that all these patterns are in there. But then I realized, say you've got a chromatic run over like one beat. Well, you get all the patterns, because you can shuffle the notes and you can find any three-chord grouping. So obviously, in that section, we're not hearing it in that way. So that's a good question, and I think we need theorists to sort of duke that one out. So maybe you and Lee can talk about that and get back to me at lunch. Yeah. There's a hand over there. Finn. Oh, Finn.
This reminds me of a project I did in my undergrad that was, where I wanted something like this in terms of being able to say it's very reassuring to see that the distributions you have, or at least for this piece, do support those that are chosen in the analysis. But what the approach that I ended up taking in looking at actually the first of the canopies and the second was to look at onsets rather than sustained note sequences. And I didn't do an exhaustive search in that way. I was looking for desperate things as opposed to exact.
So you just took like notes that had simultaneous onsets?
No, I had onset sequences. So the order had to be the same, and there had to be there was a sort of a window of flexibility in which it was a dynamic programming essentially, where I tried to fit sequences within a certain range of each other that then could potentially be associated with this melodic playing of segments rather than a vertical simultaneity. The results don't end up looking as pretty as what you showed, so I don't know what that means about the piece or the analyses, but it's nice to take these computational tools to this type of.
Yeah. Well, based on my limited, I think, one meeting attending of SMT, I think the prettier the analysis, the more important. So, yeah, I don't really know. And you could, in principle, do that kind of thing here because every note's an object and everything gets thrown into a bucket, so you can then check, if the onsets are the same. So I think there'd be a number of cool analyses that could be done. I just ended up no longer applying with them, unfortunately.
Isn't it fair to say that finding of all those patterns accords pretty well with how the music is perceived in any case? So in that sense, it is telling you something about perception anyway, even if you get all that noise?
This one instance is sort of consistent with what is talked about as being the most prominent pattern. So it's possible that it does. It's also possible that it does not. I mean, it probably does because it worked out here the way I thought it would, but I suspect you could throw other pieces in and find things that are different. What that would necessarily mean, again, that's more of like a...
I just mean the general level of noise. If you just throw it at somebody who isn't a theorist and just ask them what that...
Probably. I mean, I guess it sort of goes to some of the corpus analysis stuff that Davey was talking about. It seems like it's sticking out above that. At the time, I didn't have the statistical background to know necessarily what that meant. I just got really weirded out by the fact that there's these thousands of patterns, and I thought, I thought Scott Lipscomb's one semester intro to music perception course would help work this out, and unfortunately he let me down because it turns out it takes much more time than that. But speaking of time, I don't want to go over time. I guess we are wrapped up. So thank you very much, and I'd be happy to talk with you later on today.